So first of all, let's understand that when a 250 volt DC shunt motor, that means the supply of this motor is 250 volts, was run at the rated voltage at no load at the rated speed. So this motor runs at no load condition, right, and at rated voltage. So this is the condition, no load condition and rated voltage at rated speed. The input line current found to be 4.4 ampere. So IL, input line current, is 4.4 ampere. The next is the effective armature resistance and the field resistance were found to be 0.6 ohm and 250 ohm. So effective armature resistance, that is RA, and that is found to be 0.6 ohm. The next is effective field resistance, and we call it RF, and that is 250 ohm. Now find the output HP. So now we are going to write data to find. What data we need to find, we are going to calculate that thing. So data to find, and in data to find we need to calculate output HP. So P, and we need to calculate it in HP. And efficiency when motor draws line current of 40 ampere. So the next thing we need to calculate, that is efficiency. So we need to calculate these two things, power and efficiency. And efficiency is when current draws 40 ampere, when line current is 40 ampere. So this thing we need to calculate. So now let's start with the solution. So now we have all the necessary data. This is our shunt motor, right? So let me draw the diagram of a shunt motor. This is the shunt field winding, armature, right? Over here we provide supply, that is Vs, between these two terminals. This is the IL line current. This will become IA armature current, and this will become IF field current. RA will be the armature resistance and RF will be the field resistance. So this is the shunt field DC motor. Now what we need to calculate, first of all we need to calculate the output power, right? What will be the output power? So let me write the equation for output power. We do not have direct an equation to calculate the output power, right? But in context with these two things, let me place something over here. The equation for efficiency is output divided by input, right? The equation for efficiency is output divided by input. Now observe the data given to us. From this we can write this equation in another manner, and that manner is, actually output is input plus losses. We can rearrange this equation as input minus losses and divided by input. So this is the way by which you can calculate the efficiency. And if we want to calculate the output, we can write input minus losses. There are two types of loss, right? So we can calculate output using this equation. Output is equal to input minus losses. Now how we can calculate the input? We have the conditions given to us, supply voltage and line current, right? So using this equation we can calculate the input power. Once we have the input power, we need to calculate the losses. If we have the losses, adding these two together, we can calculate the output. So first of all, let's go to calculate the output. So now to calculate the output, what do we require? We require to know all these three currents. This is the first condition. In the first condition, IL is equal to 4.4 ampere. Now we need to calculate the shunt field current. The supply voltage is 250 volt, 250 volt across this field winding, right? So what is the IF? IF will be Vs divided by Rf. Vs is the 250 volts and Rf is 250 ohm. So IF will be 1 ampere. Now we have the total line current. This line current is divided into two sections, right? Let me write this thing over here. Place this thing in a box. We are going to use this later on. Now focus over here. IL line current is IA plus IF. Now we want IA, armature current. So IA is equal to IL minus IF. IL is 4.4 ampere and IF is 1. So we can get 3.4 ampere of armature current. IA is equal to 3.4 ampere. So two quantities we need to calculate: IF field current and IF armature current. So these two quantities we have calculated, right? Now we need to be focused on the losses. Why? Because once we are ready with the losses, we just calculate the input and place it and calculate the output. So first of all, we are going to calculate no load input power. So no load input power. So what will be the equation for no load input power? Is the total voltage multiplied by no load current, and the total voltage is V into IL is equal to IL0, no load current. Observe over here that input line current found to be 4.4 ampere when the machine runs at no load. So at no load, input line current is 4.4 ampere. So we have the value of this line current. So it's 250 multiplied by 4.4, and that is going to give us 250 multiplied by 4.4, 1100. 1100. So this is the no load loss. Now if we subtract the copper loss, Cu loss, and Cu loss is Ia0 square into Ra. Ia0 square, Ia is 3.4, so square of 3.4 multiplied by Ra. Ra is 0.6, so multiply by 0.6, and that's going to get us 3.4 multiplied by 3.4 multiplied by 0.6, that gives us 6.936. We will take it as 6.9, right? So this is 6.9 watt. No load copper loss and no load input power loss. So this is total no load loss, right? Now from this calculate the constant losses, because this is the total no load loss, right? Total no load loss. Over here we have calculated copper loss, and now we are going to calculate the constant loss. Constant loss means core loss, which is invariable in any condition. So now we are going to calculate the core loss. Very good, Kevin and Janish, you have got it correctly. Even Janish has previously also calculated it correctly. Good effort by students. Now we are going to calculate the constant loss. The constant loss is known as WC, which is equal to input power total no load loss, that is VIL0 minus no load copper loss, that is this IA0 square into RA, which is equal to 1100 minus 6.9. So this is 1100 minus 6.9, that gives us 1093 watt, right? So 1093 watt is the constant loss. So the term we want to calculate constant loss, that is 1093 watt. So this is the first condition we have got, which is constant loss. See, because this loss over here is made up of two loss. One is constant loss and the another is CU loss. Constant loss means core loss and the another loss, CU loss, means copper loss. Constant loss is constant in all the condition, and CU loss is variable, that depends on the load condition. So first of all we got this constant loss, and now we are going to calculate this copper loss. So let's calculate the copper loss. To calculate the copper loss, we need to focus on this condition, because we want to calculate the efficiency at 40 ampere line current and the output power at 40 ampere line current. So we are going to calculate the input power and output power at this condition. So when supply draws 40 ampere, the input power is V into I. V is 250 volt and I is 40 ampere. This is very simple to calculate. 250 into 40, that's going to give us 10,000 watt. So this 10,000 watt is total input power. Very good, Janice, Kevin, good. So this is input power, right? Now from this input power we are going to calculate the CU loss, right? And to calculate CU loss, what do we need to calculate? The CU loss. The equation for CU loss is IA square RA, and now we want this IA square. What is the equation for the IA square? It's this: IA is equal to IL minus IF. Initially IL was 4.4, but now IL is 40. IF is 1 ampere. So armature current is 39 ampere. So we need to use this 39 ampere in this equation. So 39 square into RA, which is 0.6. So 39 into 39 multiplied by 0.6, which is equal to 916.2. 916.2 watt, which is CU loss. So we have the input power, we have the CU loss, we already calculated the constant loss, right? So the total losses is equal to IA square RA plus WC, right? IA square RA we have calculated 916.2 plus WC 1093, and the total of these two plus 1093 2005.6. It's not 1916.2. okay, so 2005.6 2005.6 watt, that is the total losses. So we have calculated the total losses. Very good, Parth and Kamlesh, good, you have got it correctly, that's nice. So the total losses we have got it as 2005.7 watt, and now finally we are going to calculate the output, because we have input total, this is the total input, we know the total input, we know the total losses. So using this we can calculate the output. Let's calculate it. It is our output. Output is basically input minus losses. Our input is 10,000 watt minus total losses are 2005.6 minus 10,000, that gives us 7994.4. so output power is 7994.4 watt. So this is the first finding, right? Output. But this is not the exact first finding, because we need to calculate this output in HP. So now we are going to convert this output in HP. 7994.4 divided by 735.5 divided by 735.5. sorry, it's not divided. 7994.4 divided by 735.5, that is 10.869. so 10.87 HP. so this is our output 10.87 HP. so this is our first exact finding, and very good, Kevin and Saurabh, you have calculated it correctly. Now we are going to calculate the efficiency, right? The equation for efficiency is nothing but the output divided by input. We have calculated output over here, and that is 7994.4, and our total input is 10,000 watt. so the efficiency will be 7994.4 divided by 10,000. so 0.7994, and if we want to convert this in percentage, the percentage efficiency is 79.94%, and this is our second finding. This is the second thing which we need to find.